All right, today we're starting chapter 8 on Earth. This is a famous image called the blue marble image because, well, the Earth is beautiful blue color due to its mostly being covered in those ocean waters. This was taken from space by the Apollo 17 astronauts. And it's one of the rare images in which you see the entire face of the Earth illuminated. So the sun would have been behind the astronauts so that you see this whole face of the Earth, the face that's facing us, illuminated. Now, the interior structure of the Earth is what we talk about here in section 8.1. And the main way that we study the interior of the Earth is through what's called seismology, the study of earthquakes. You can measure how long it takes earthquakes to travel across the surface of the Earth, the vibrations from them, and down into the Earth and up out of the Earth. And from their travel times from one place on the surface of the Earth to another, you can learn about what the interior of the Earth is like. Because if you make different models of your Earth where you have different density profiles, that is, different density as a function of position, it takes different amount of time for those vibrations to go down and then come back out again. And so by studying enough earthquakes, you can build up these kinds of models. In the center of the Earth, that's where you have the highest density material, the nickel and the iron, right? Getting close to not quite 10 grams per cubic centimeter. The very interior, the inner core, is solid. You do have a little bit of the outer core that's shown here as well, which is more liquid. Now, most of the volume of the Earth is inside of the mantle. And people have this misconception that the mantle is liquid as well, that it's just magma flowing around in there. That's not at all the way it is. Yes, there are hot pockets within the Earth where you have rocks in liquid form. That's what we call magma when it's underground. If it comes up above ground, we'll call it lava. But the vast majority of the Earth is solid, even within the mantle. There you have more moderate density materials, right, that are rocks made out of silicon and oxygen and other elements. The crust is the topmost few miles or several miles. And that's made up of rocky material that's like granite, basalt. Basalt is formed when you have running lava come out of volcanoes and then it solidifies. So those are basaltic rocks. About 90% of the lava that you get out of volcanoes is of this more runny basaltic type. And then granite is another type of rock as well. Now notice as you go down deeper and deeper, we say it gets to denser and denser materials. Iron is one of the most dense materials there is. And that process of differentiation is why that occurs. If you've ever put a rock inside of a pool or a pond, you know that the rock, being more dense than the water it displaces, falls. But if you put some piece of wood there within the water, it's less dense than the water it displaces, and it's buoyed upward, right? So there's a natural tendency for materials to separate themselves by density. The more dense materials will sink down and the less dense materials will float up to the top. And while the Earth formed 4.5 billion years ago, the differentiation occurred, and that more heavy, those denser materials sank down towards the center, ultimately forming the core, and the lighter materials rose up to the surface. Now that uppermost several miles of the crust, here you can see that with this satellite imagery. The water is here shown in blue, with the darker blues representing the deeper portions. The dry land is shown in shades of green and brown, and Antarctica and Greenland are shown in ice there. This is an image of the Earth's crust determined both by satellite imagery as well as ocean floor radar mapping. We've talked about radio waves being a form of light. Radar is when we generate this light, these radio waves. You might get some big antenna that you're using to emit the light, and you run electricity back and forth through this. And then that oscillating electric current makes a long wavelength radar pulse. And then that radar pulse, you could say, send down to the base of the ocean, time how long it gets there to bounce back, and you measure how deep the ocean is by the travel time of that particular radar. Now, the Earth has a magnetic field. Magnetic fields are caused by moving charged particles. And there's an image on the left here which shows us a bar magnet, like a ceramic refrigerator magnet, or maybe it's a chunk of iron. And it's got a North Pole and a South Pole. And there are these kind of lines that are drawn out of it that are coming around from the North Pole to the South Pole, or from the South Pole to the North Pole. And I want to show you here, I've got over set up on the side, I have a little iron magnet. I've got a piece of plastic, and I've got some iron filings, right? So these are just little shavings of iron. Iron is nice because it responds to magnetic fields. And once you magnetize iron, it stays magnetized. And so I'm going to just go ahead and shake these iron filings over top of this bar magnet. And what you're going to see is that they don't just randomly fall and align themselves in some random orientation, but rather you start to see patterns develop in terms of how they align themselves. Can you see that here, how they kind of loop around and then come back in here and comes back in? Oh, look, it's even sticking. Some of these iron filings are even sticking to my tip of my scissors. But what's going on is that that bar magnet is generating a magnetic field. And then the iron filings are lining up with that magnetic field. So when we talk about magnetic fields, it often sometimes when you're first learning about them feels like a very abstract concept because, you know, you don't really see the magnetic field lines. Here you're seeing them in a sense because the iron filings line up. In a sense, you can say, you can define the direction that a magnetic field points by the direction that the iron filing would point. And where those magnetic field lines are packed closely together, that's where the magnetic field is strong. Where those magnetic field lines start to spread out from one another, that's where the magnetic field is weakest. And you might say, well, you said a moment ago that magnetic fields are caused by moving charged particles. I don't see anything moving in that bar magnet there to cause the magnetic fields. What's the deal with that? Well, there are charges that are moving on the atomic scale. In ferromagnetic materials like iron, you have an unpaired electron that is orbiting around, right? You have all these electrons going around. And most of the time, you know, you might have one electron going this way, counterclockwise as viewed from above, and the other electron going clockwise as viewed from above, right? If you think about it in this semi-classical idea where they're orbiting the nucleus. Or if you describe it in quantum mechanics, some of them have positive angular momentum along a certain axis, others have negative. But there's one electron which is extra, and it's orbiting around. And what happens is the way iron interacts with neighboring iron is that if this one electron is orbiting around in a certain way, then its neighbor is more likely to orbit around in the same way. And then another neighbor orbits around in the same way. So you get this abundance of extra electrons. They're all orbiting in the same way. And effectively, in terms of the current, it's as if there's current running around, making big loops throughout the entire material. And so although no one electron makes a big loop around the iron magnet, the combined effects of the many electrons in their orbitals is the same. And so those moving charged electrons is what generates this magnetic field. And that magnetic field pushes on other moving charged particles. In the middle here, we have a solenoid. You know, when you get in a car and you hit the button to unlock the door, or maybe to lock the door, and you hear it kind of like makes a little bit of a sound and then click. What's going on there is when you hit that button, you close an electric circuit. and you start running electricity through a solenoid, a coil, just a wire wrapped around a cylinder. And in addition, there would be a little bar magnet, like a little piece of iron in there. And when you start running the electricity through that coil, you generate a magnetic field inside the cylinder that pulls the bar magnet in. It physically moves it. And that activates the locking mechanism. When that magnet gets pulled down, something else gets shot over and you lock the door. And then if you let the bar magnet get pulled back out the other way, you unlock the door. So there's an example of running electricity through a circuit, through a coil in this case, and making a magnetic field. Now, why are we talking about these things? The Earth itself has a magnetic field. Remember, we said that the outer core was molten and liquid. It's easier for charges to flow around in there. Deep in the Earth's interior, you have electrons that are flowing around. That's the only way you can explain having the magnetic field of the Earth. So when you go out and you're hiking through the woods and you've got your compass, that compass needle is really just a piece of iron. And what's happening there is that it's lining up with the Earth's magnetic field that was generated by charged particles in its interior moving around. And it turns out that the geographic North Pole is close to the magnetic South Pole of the Earth. And so your needle will point up towards the geographic North Pole, the magnetic South Pole of the Earth. In the same way that you saw a moment ago, the iron filings lining up with the magnetic field of that bar magnet, your compass needle will line up with the Earth's magnetic field. Comments and questions on this? I'm not sure that it matters so much about the magnetic field. I think what is more important is that there's enough pressure from the outside. When you have two substances that are the same in many regards, let's say it's the same temperature, etc., but you put one under higher pressure than the other, you can solidify that object just by having pushed in on it really hard. So, the freezing point of water, depends on what the atmospheric pressure is. In general, for most substances, the more pressure you put on it, the more likely it's going to be in a solid, the higher the melting point would be in terms of the temperature. So I think that's the biggest difference between the inner and outer cores, is the higher pressure in the center. And when you wonder about why, why is it higher pressure? What's going on there is you're supporting the weight of everything above you. If you imagine a pile of pillows, the pillows at the top are analogous to the crust of the Earth. The pillows at the bottom are analogous to the core. And the pillows at the top, they don't have very many pillows on top of them to compress them. But the pillows at the bottom have got the weight of everything above it pushing down on it. That's why you get those really high pressures in cores, because you have to support the weight of everything above. So the Earth has this magnetic field. Its magnetosphere is that magnetic field throughout and around the Earth. And it extends out to large distances. Here's a cross-sectional view of that Earth's magnetic field. And remember, I told you that magnetic fields push on charged particles. So what happens is you have your solar wind. The solar wind is like electrons and protons and helium nuclei that are getting blown out from the sun, really low density, but high speeds in all directions. And those solar wind particles, they'll come and they'll hit upon the magnetic field, and that pushes them sideways. So in a sense, that magnetosphere of the Earth is a protective layer. It prevents the solar wind from coming down in and striking up against the Earth's atmosphere, for the most part. When charged particles come and follow the line of a magnetic field, right, then the force from that magnetic field is zero. If you want to maximize the force of the magnetic field, let's say this finger represents the magnetic field. If you want to maximize the force that it has, on some charged particle of a given speed, bring that charged particle in perpendicular to the magnetic field, then it gets pushed sideways. If the charged particle is running right along the magnetic field in the same direction as it actually ends up feeling no force. So notice how the magnetic field lines are coming down into the North Pole and out of the South Pole, right? So if you do get charged particles coming in towards the North or South Poles, it's easier for them to get down deep and actually, in some cases, strike the atmosphere. That's why we have aurorae, you know, like the aurora borealis are the northern lights. Those occur when charged particles in the solar wind strike the upper atmosphere, excite the atmospheric gases, and then as the electrons fall back down onto the gases, atoms and molecules, you get light that's emitted, and you see these wispy light features in the sky. The Van Allen belts are labeled here in this image. Those are zones of energetic charged particles that have been trapped in a circular trajectory around the Earth. And when you launch, for example, astronauts to space, like the Apollo astronauts when they went to the moon, for example, had to pass through the Van Allen belts on the way. Now, let's talk a little bit more about the Earth's crust. It's largely made of this igneous rock. Igneous rock is rock that forms when liquid lava cools and solidifies. So remember, if the rock is underground and liquid, we call it magma. It'll erupt through a volcano, and then when it's flowing along the surface, we'll call it lava. And then when it solidifies, we'll call it an igneous rock. Now, most igneous rock is basaltic, and that is a type of rock that forms when the lava is kind of runny. It runs out over long distances. It's not very viscous. Like when I think of something that's viscous, I think about honey. You know, if I try to pour honey out of a bottle, it just slowly blobs along, doesn't really flow. Water's a lot less viscous. It's real runny. It just, if I try to pour it out of a bottle, it just squirt right on out, run over the floor and everything. So when you have that runny kind of lava and it solidifies, that makes basaltic rocks. So I picked a few time-lapse videos to show you here today. Actually, I think maybe this is the only time-lapse video. But this is some lava flows from Hawaii. This first time lapse will be at 20 times natural speed. But you can get a feel here for lava flowing on the side of a volcano in Hawaii. It's kind of interesting dynamics for how it plays out. There's a lot of motion in that lava going on under the surface that you see that kind of carries that surface along. But you can tell from the red color there that it's quite hot. You can see some grasses in the foreground there that give you a little bit of a sense of the scale of how large this lava is here. And just a few days ago, March 19th in the evening, in fact, there was a volcano in Iceland that hadn't for, some say, 6,000 years erupted. And so given that that's been in the news here lately, let me also bring that up for you. It erupted that night of March 19th, and the first video that I'll show you is at nighttime, and so you can really see that lava flowing there and just how bright it is given its intense heat. There's the eruption as it actually spews that lava out of the top of the volcano. And then in a moment here, we'll switch over. This is a helicopter video. You can see some of the structure of the helicopter in the foreground there. And now you can see it in daytime on the next day. This is on March 20th. It's still erupting. Now, the nearest city to this volcano is 6 miles away, so it's relatively safe as long as you keep your safe distance from it. And it's 20 miles away from the capital of Iceland. But you can see that this is a process. Volcanic eruptions, this is a process that happens all the time. While most of the volume of the Earth is solid, there are little pockets where it heats up inside. And if those pockets break forward and forth from the surface of the Earth, then we can have these volcanic eruptions. So this is an example, Earth is, of a geologically active system. Its surface is being reformed by these volcanic eruptions gradually with time. Here's a thought question for you. Do rocks stretch? No, rock is rigid and cannot deform without breaking. Yes, but only if it is molten rock. And yes, rock under strain may slowly deform. Why don't you go ahead and take a stab at that one? So here we go. 72% of you are saying yes. Well, you're all saying yes, but 72% of you are saying yes, rock under strain may slowly deform. And indeed, that is the right idea. It takes longer amounts of time, but even rock is not perfectly rigid. If it's being pushed, you can stretch it out over long time periods. It kind of acts like silly putty. Silly putty is a neat kind of substance. You know, if you just kind of have it in your hand, you can pull it apart and it stretches. But over shorter times, it acts very rigidly. If you take silly putty and you throw it and smash it into the ground, it'll shatter into pieces. It won't just like blob up on the ground. And I picked out another YouTube video here to demonstrate this. In this particular video, they're dropping a big ball of silly putty off the roof of a building. And I want you to watch how that silly putty behaves when it hits the ground. 3, 2, 1. Oh, man. Bam! Look how it shatters, right? Now, when they zoom in on this piece of silly putty, you got to watch carefully. But look, it's gradually becoming flatter and flatter, right? So over that longer time, it was slowing down. I'll show you the end of that video again. So short time scales, it's nice and rigid, fragments. But if you look over longer time scales, watch again here, you'll see it kind of flattens out just slowly. Look at how it's curved at the bottom, getting closer and closer to the ground there. There you go. So in general, that's how rocks behave, but the time scales that it takes for them to stretch, to be pushed around, can be millions of years. And so inside of this mantle, even though it's rigid, you have what are called convection cells. And what's happening is that material will gradually rise up and then fall back down again. It's really the same kind of physics as what happens when you boil a pot of water. When you boil a pot of water, you got a flame underneath your pot. It heats up the water at the bottom. That hotter water rises up, releases its energy, and then falls back down. And then it gets heated up again, rises up, and you get these convective cells. And it's the same thing here happening inside of the mantle. It just happens over long amounts of time. Now, if you look at how that's going to affect the crust, or more generally, the lithosphere is the crust and the uppermost portion of the mantle that is really just perfectly rigid, where the rock is really so solidified that the convective cells don't penetrate that region. And if you look at the convective cells, how they push on the lithosphere, including the crust, like look at these two cells. This one is moving at the top from left to right. This one is moving from right to left. So it's pushing in on this central location here. And so what happens is mountain ranges would rise up as the lithosphere and the crust get pushed together at that location, and the material's got to go somewhere. So it goes up and forms those mountain ranges. Or if you look at these two convective cells on the right, notice this one is counterclockwise, while this one is clockwise. So they're both pushing away from this central region. And so there you have an extension. The material gets stretched out. And so that would cause cracks and valleys and other surface features similar to that. So this is a geologically active planet that we live on. over on the right, you can kind of see that there are earthquakes that have been shown here with these yellow dots. And these earthquakes all lie along the boundaries of these tectonic plates. Those convective cells are pushing on little fragments or plates on the surface of the earth, pushing them toward one another in some places and away from one another in other places. And over time, that means that the continents themselves move around. So if you look in the lower right, you can see that South America and Africa and North America and Europe long ago were actually all together in one supercontinent. And that plate tectonics, this motion of the plates of the earth, have pushed those continents apart from one another over time. The kinds of speeds that these plates are moving are about an inch a year or so is a typical continental plate speed. That's about the rate at which the hair, well, no, that your hair probably grows a little faster than that. That's probably the rate at which your fingernails grow on your fingers. There's a question in the chat. How long did it take for them to be in the positions they are in today? Pangaea is the name of the supercontinent, and it's about 300 million years ago to about 180 million years ago. So on the order of hundreds of millions of years. Remember, for comparison, the dinosaurs became extinct about 65 million years ago. And so that helps to put in perspective how long ago we were talking. Follow-up questions and comments? Based on how the plates have moved in the past, can scientists predict what they would look like, say, 100 million years from now? And the answer to some extent is yes, but the farther you try to look into the future, the harder it becomes. But yes, there are geoscientists who try to model this kind of behavior, and they could make predictions about what it would look like in the future. Paleontology is the study of fossil records, and you can look at, for example, fossils that are on the east coast of South America and the west coast of Africa and see correlations and know that those land masses were in contact with one another. Down at the bottom here, I included a link to the USGS website. And this keeps track of where and when the earthquakes occur. Right now, I have it so that I'm showing you all the earthquakes of any magnitude within the last 30 days from across the earth. And the little red boundaries there are the plate tectonic boundaries we were just talking about. And you can see that the vast majority of these earthquakes are forming along those boundaries. That's not surprising, because where the mass is being pushed up against other mass, or where you have those regions of extension, there the Earth's crust is more unstable, you're more likely to have an earthquake as a result. If we zoom in on Earth, you can see, like along the San Andreas Fault on the western portion of California, that's where a lot of the earthquakes are. There's also quite a few earthquakes you can see here in good old Oklahoma. Anybody want to hazard a guess why there's so many earthquakes in Oklahoma, despite the fact that that's pretty far from any plate boundary? I'll give you a few seconds to chat it in there. I see someone chatted fracking. That is it, fracking, right? That's where you put high pressure water underground to try to get out natural resources. And so that can make the ground unstable, that can cause earthquakes. Now, these magnitudes you see listed over here, 2.5 and up, 4 and up, that's a logarithmic scale. You've heard of this before, the Richter scale, for measuring the strength of earthquakes. If there's like here's all the 2.5 and up earthquakes in the last 30 days, you can see there's a lot of them. They're not really strong enough to make the news unless you were like right on top of those earthquakes and it happened in your hometown. You probably wouldn't know about it. But once you get to like 4.5 magnitude and up, then you'll read about it in the papers. But you can see that there's a 4.5 and up magnitude earthquakes here in the last 30 days. Even in the last 7 days, if we look across the United States, well, that's all magnitudes, 2.5 magnitude. Let's go to 4.5 and up. See, only really one magnitude 4.5 or up in the last 7 days. But these earthquakes are happening all the time. They're not uncommon. The uncommon ones are, at magnitude 5 and up, magnitude 6. That's where you often can then start causing damages to buildings and so on. Comments and questions on this? All right, so there's a question. I think it was last year that Ohio had an earthquake because of fracking. I didn't know about that, but indeed it did happen back in 2014. I was in California once, and the only time I ever experienced an earthquake. And yeah, I was in the hotel up on about the 3rd floor or so, and you could just hear the furniture on the side, ding, 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 right up against the wall. It wasn't a very big earthquake, but you knew it was happening. So here we'll talk about rift and subduction zones. The subduction is this process where material gets transported down into the mantle. So imagine you have these two parts of two different plates that are being pushed toward one another. One of the plates is going to go down under the other. The other might get pushed up to help make the mountain ranges. But the part that's going down under, that's in the subduction zone. And that subduction zone will then take the material from the crust and push it down into the mantle. If there were any craters on it or other interesting geological features, it could then be destroyed as you bring it down into that upper mantle. These rift and subduction zones are the regions where new crust is formed and old crust is destroyed as part of the cycle of plate tectonics. If you go to the middle of the Atlantic Ocean, you have the mid-Atlantic ridge. There, the two plates are being pulled apart from one another, and material is flowing up from underneath, creating new seafloor as the North American and South American continents move away from Europe and Africa, right? New material is being made at that mid-Atlantic ridge gradually as material comes up. So here you can see some mid-ocean rift zone like the mid-Atlantic ridge. Notice that black arrow showing that this plate on the left is moving to the left. This plate on the right is on another plate moving to the right. Material from underneath comes up and makes new ocean floor. And down here we have the subduction. See how this plate is being pushed in toward another plate, and then it gets pushed downward into the upper mantle. The San Andreas Fault, here's an airplane image along that fault line there. That's the one in Western California that we had seen on the maps earlier. The fault here is running up along the right edge of the photo. And what happens along that fault line is that you can have slippage. So like, it doesn't just have to be the plates are moving directly toward or away from one another. They can go transverse, sideways to one another as well. And if you look carefully at this image, there are certain regions where you can kind of imagine that having happened. Here's a mountain range with these sharp mountain peaks. These have been sculpted by glaciers. We'll talk a little bit about how the Earth can go through ice ages, where large portions of the Earth can be covered by ice. And ice is very powerful. You know, it pushes up against rocks. It can cut into those rocks and form these kind of sharp features like you see here. Also, because Earth has an atmosphere, something that we're going to be discussing in more detail this week, you get erosion processes from rain and wind sand particles blowing up. These are all processes that shape the surface of the Earth. And so the Earth's surface now is not at all like it was 4.5 billion years ago. Because of subduction, because of creation of new seafloor, because of erosion, because of glaciers receding and moving in and out over time, the surface of the Earth has been reshaped. Geologically dead planets like Mercury, or geologically dead worlds like the Moon, their surfaces show you a lot more history because they don't have these same kind of processes destroying the features on their surface. Now, I asked you to skim section 8.3. I don't care. I don't need you to memorize what an ionosphere is and a mesosphere and a stratosphere and all that stuff. What do you need to know? It would be nice to know that there's ozone in the upper portions of our atmosphere. Ozone is O3. Oxygen, oxygen, oxygen. The oxygen that we breathe in the air here, that's O2, diatomic oxygen, two oxygens bound together. O3 is occurring when you get an O2, maybe a cosmic ray particle comes along, splits the O2 up into two individual O's, and then one of those O's loosely binds to an O2, makes your O3, that's ozone. Ozone is nice because it shields us from ultraviolet radiation. And when I was back in high school in the 80s, you know, the big thing wasn't global warming, it was ozone depletion. Those are two things people often confuse with one another. They're not the same. Global warming is, you know, climate change, the Earth is getting hotter. We're going to be talking about that in detail next time. Ozone depletion is, well, if you emit, like we were doing back in the 80s, chlorofluorocarbons or other things that you have in aerosol cans, but we don't have that used any longer, that can destroy the ozone in the upper atmosphere, and then ultraviolet radiation can get through. That's cancer causing and so on. So nice to know that there's ozone. Nice to know that our clouds are H2O clouds. You have little dust grains that water droplets can form around, and they're kind of then floating up there in space, making those, not space, but in the atmosphere, making those H2O clouds. As you go up higher in the atmosphere, the density of the air gets less. It becomes less and less dense. And at least at first, through the first 40 or so, 30 to 40 kilometers, the air gets colder as you go up higher and higher and higher. Then once you get up above 40 kilometers, this is really low density air that we're talking about. Still dense enough that that's where the meteors occur. That's where they burn up. If you make it above 100 kilometers, which is 62 miles, then you are considered an astronaut. That's what space is defined to be, 100 kilometers. At that altitude, there's very little atmosphere left. Here's a Hurricane Irene, imaged in 2011, shortly before that storm hit the East Coast. And the combination of the Earth's rotation and its tilt is what causes these kind of weather patterns. When you're on a rotating planet, you have what's called a Coriolis force. It's easy enough to visualize a Coriolis force, what it means. Like, you know, imagine this Earth here, this just keeps rotating. And if you fire something off the North Pole, the Earth rotates underneath it. So as viewed from the Earth, the missile you fired seems to deviate to the west. Or if you were on the equator and you launched something northward, on the equator, you're spinning pretty fast before you launch your missile north. And then as it goes northward, the missile starts to go over regions of the Earth that aren't spinning as quickly because it's got a smaller circle to spin around in just one day. If you were on the North Pole, you're just spinning around in a fixed location, no rotational velocity. If you're on the equator, you got this big 25,000 mile circuit to make in 24 hours. So the missile fired off of the equator is moving really fast from west to east, just due to the Earth's rotation when it's launched. And when it gets above the northern latitudes that weren't moving as fast from west to east, you'll see that it deviates again, it'll deviate off to the right. It had been moving very quickly to the east, so it gets above the landmass, moving more east to the landmass than what's beneath it, than it would have if it had just gone straight north to south. So in the northern hemisphere, this Coriolis force always bends materials that are flying around to the right. And if you have a high pressure system, the wind will flow out of it. If you have a low pressure system, wind will flow in toward that low pressure system. And as the wind flows in, it bends to the right. And you end up then getting hurricanes as a result when winds flow in towards those low pressure systems due to the Coriolis force, which is due to the Earth's rotation. Now, in the last section I asked you to look at, I asked you to look at the beginning part of it. We start to talk about life, chemical evolution, and climate change. We'll be reserving climate change for the most part till next time. Maybe we'll have a few moments to say something about it today. But here on the image on the left, figure 8.15, we have some fossilized stromatolites. And stromatolites exist to this day. They're microorganisms that kind of live in these colonies here. This is in Australia, and you can see there's some water here, and at different tides, the water may come into different levels on these stromatolites. But in these living colonies, the stromatolites, they try to kind of build on top of one another to get up towards the light. And so they end up having this layered structure. And if you were to cut apart one of these and take a cross section of it, you'd see the same kind of features that you see here in this fossilized rock. But this rock is 3 billion years old. This is modern day. This is 3 billion year old rock. And so the idea is that, oh, there were stromatolite colonies that existed 3 billion years ago. So life on Earth has been around for, just from this alone, at least 3 billion years. In fact, we think it's closer to 4 billion years. How did life arise on Earth? We may never really quite know. There are experiments that are done, like the Miller-Urey experiment, where you take the materials that are available in the early Earth, in the early Earth's atmosphere, and you show that through shocking it, like you might have with volcanic eruption, that you can spontaneously start to form organic molecules, the kind of things that are used to make living organisms. No one has ever created life in the lab. No one has ever started with organic molecules and then created something that was living. If you look at the DNA, the deoxyribonucleic acid that is inside of all these living organisms, you can see patterns, and you can start to build what's shown here and called the tree of life. There are different branches to this tree. The three main domains are shown here. The plants and the animals, they're all just on one of these domains. But if you look, there's all these other kinds of life as well. Bacteria, for example. And so as you go closer and closer to this base of the tree of life, you are looking towards that common ancestor. And the idea is that life must have formed in some simple way, some microorganism that then through time evolved into these main different branches, ultimately ending with us, the humans, the Homo sapiens, as well as all the others. But if you look at the DNA of a tree or a fish, in many ways, it's similar DNA to what we as people have. And if you look at the DNA of something like a chimpanzee, it's even more similar. I think it's somewhere around 2% or so, like the difference in DNA between a human and a chimpanzee, somewhere around 2% different, something like that.